Welcome to Chapter 6, Section 7. This section is about volume in moles and Avogadro's law. The three basketballs that you see here actually represent what a mole of a gas, about what a mole of a gas would take up with respect to volume. It would take up fill about three basketballs. Avogadro's law is relating volume in moles, and to me one of the more common sense laws that typically makes sense to most students. Basically it says that if you increase the number of moles or the amount of gas that you have, then you're going to increase the volume. So the more you have, the bigger the volume, which makes sense. Okay, and so here's a relationship here, that they have a direct relationship. So if you have 2 moles versus 1 mole of gas, then you're going to occupy 2 liters versus 1 liter here. So the more moles, the more the volume. One of the main concepts under Avogadro's law is standard temperature and pressure and molar volume. Standard temperature and pressure is basically just values that we use for ideal gas laws and for ideal gases, and it states that the standard temperature for a gas is going to be 0 degrees or 273 K, which we normally use 273 K since we need Kelvin as our units for gas laws. And for pressure, it's 1 atm or 760 millimeters mercury. So if you have a reaction and you're told that it's done under conditions of STP, standard temperature and pressure, then you know that is 273 K and 1 atm. At STP, 1 mole of any gas occupies a volume of 22.4 liters, which this is called the molar volume. This is very unique to gases because for your liquids and your solids, there's no way for us to relate 1 mole of a liquid or solid to other moles of a different liquid or solid. But for gases, if you're at standard temperature and pressure, 1 mole of any gas, it has to be an ideal gas, but the gases that you guys will be looking at and studying are all ideal gases. It occupies a volume of 22.4 liters. Okay, so if we think about that, we can relate back to those basketballs. That's about 22.4 liters of gas in those 3 basketballs. Okay, and so if we look at this, we can come up with a conversion factor, just like we did in Chapter 5, where we had grams to moles. Here we're going to have liters to moles. So for every 22.4 liters, that is per 1 mole of gas. We can set up our ratios here. Or we can invert that, and we would have 1 mole per every 22.4 liters. So if we look at these balloons, we have helium in the yellow balloon, oxygen in the red, nitrogen in the green. So it doesn't matter what the gas is. At STP, 273 Kelvin and 1 atm, we have 1 mole of helium, of oxygen, and nitrogen in those balloons, and they have the same volume. The volume is 22.4 liters. Okay, now our mass is different because they have a different mass with respect to the periodic table when we add up their atomic weights. Okay, but the mole, if there's 1 mole of gas, it will take up a volume of 22.4 liters. Okay, so how can we use molar volume in our conversion factors or from converting from one thing to another? Basically, it's the same as we have been doing. You can state what you're given and then what you need. So we can write out what we're given. We divide the plan, and then we use our conversion factor, which we've just shown is 22.4 liters per mole at STP. And then you can set up the problem and cancel your units. Okay. So if we want to know what's the volume occupied by 2.75 moles of nitrogen gas at STP. Since it's at STP, we know that we're at 1 atm, 273 K, and that the volume for 1 mole is equal to 22.4. So if we look back over here, it's equal to 22.4 liters. It's our standard molar volume. Okay, so we have a plan. We have moles. We're given moles of nitrogen, and we want to convert to volume of nitrogen. So the only way that we can do this with a common relationship is use our molar volume. So if we have 2.75 moles and we use our molar volume here, so we plug it in, okay, and we notice that, let me get my pen here, we have to use, so here's our ratios, or our conversion factors. We have to use, we could use either one, but we have to use the one that's going to plug into our equation and for us to be able to cancel our moles. So remember, we cancel diagonally, so you end up multiplying 2.75 times 22.4, and we end up with 61.6 liters. So that's the volume that would be occupied by 2.75 moles of nitrogen gas. Versus 1, we know, would be 22.4. If we had 1 mole, it's always going to be 22.4 for an ideal gas, which is what we're going to be dealing with. This is our molar volume. So it's really just a one-step calculation, and you use the standard molar volume, something that is so unique to only gases. Here are a couple problems for you to practice, so you could stop the video if you would like, and then pick back up and see if you got the answers right. So we're going to go through and work these using what we now know about the STP and molar volume. The first problem says that we have 4 grams of methane, CH4, at STP, and we want to find the volume. The only way we can relate volume and a quantity is by the molar volume. Here we're given grams. So the only difference between this and the previous problem is that we're going to have to convert from our grams to moles first, and then use this. Okay. Sorry, I think I went out for a second. But the only way that we can convert and use our standard, our molar volume, is by first converting. We're going to have to convert from grams to moles first, and then we can go to our volume by using the molar volume of a gas, which is 22.4 liters. Okay, so, and let's go ahead and just work through number 1. So we first are going to devise a plan. So we have 4 grams, and we need to find what the volume is at STP. Okay, and so this one's actually going through both problems 1 and 2. Okay, and then in problem 2, we have 8 liters of a gas, and we want to know how many grams. Okay, so for this problem, we're going to have to go from liters to moles, and then we can go to grams. Okay. Okay, so this is what we've already stated on the previous slide. So for number 1, you had to go from the mass, so we had 4 grams. We have to go to moles, and then we use the molar volume. This is the same plan I had on the previous slide. Okay, for the second problem, we have the volume. This is what we're given, so we always write out what we're given. Then we have to use the molar volume to find moles, because our molar volume doesn't find mass, it finds moles. Okay, and then we can go from moles to grams. So here we're just going from moles to grams, and we can do this just like we've done previously in Chapter 5. Okay, our conversion factors for the problem is our 22.4 liters per mole. Okay, we're trying to get from, in the first problem we've got grams, and then we've got to want to get to volume. Okay, we also need to know that in 1 mole we have 16.05 grams. So this came from the periodic table where we added up the molar mass. So we have two conversion factors that we're going to need. Okay, for the second problem, hopefully this isn't confusing doing two at one time, but we've got the same conversion factors that we need, the 22.4, and then we're also going to need our grams to mole relationship. That's our molar mass of helium. So the number 2, we're dealing with helium. Okay, so it'd be good to pause if you need to go back and look at the problems when we're doing both of them here together instead of separate. Okay, so we're going to be using one of these conversion factors here. Okay, so we have to put it together. For number 1, we were given 4 grams at STP is the key here because at standard temperature and pressure, our molar volume is 22.4. But we're given grams, so the first thing we have to do is convert to moles. So we take 4 grams and we divide through by 16 grams per 1 mole because we know that out of every time we look at the periodic table and we add up our molar mass, it's always out of 1 mole. Okay, and so our 16 grams goes on the bottom. So all this is just like chapter 5 from converting from grams to moles. Okay, and once we can cancel our grams, now we have moles on top. So we need moles in order for us to be able to plug in the molar volume. And we know that 1 mole for every 22.4 liters of any gas at STP can go in here as our conversion factor. So we have a 2-step process here. So our moles now cancel. We're left with volume on top, which is what we want to find. And so the volume of the gas would be about 5.60 liters. The second problem is different only in that we start with liters. And so we can use our liters, always write out what you know first, so 8.00 liters. And then the only common relationship we have is to go ahead and use our molar volume. Okay, so our liters will cancel. We're left with moles on top because that's what the molar volume is, 22.4 liters per 1 mole. Okay. And we know that in 1 mole, we have 4.00 grams. So this is the molar mass, or the atomic weight, of helium. If you look on the periodic table, it's 4.00. So now our moles will cancel. We're left with grams of helium on top, which is what we're trying to find. And that would be 1.43 grams of helium. So these are a couple of variations. The first was just going from using our moles and going to volume. Okay, and then the second problem, we're going from grams to moles to volume. So this was the same. This step here was the same as previously, but we had to go to grams to moles, just like we did in chapter 5. Here we're given volume, a number in this problem here, the third example, and we have 8 liters. We always write that out, and then we write out our units on the bottom. Okay, so don't forget whenever you write out what you know, you go ahead and put those same units on the bottom because you know that these have to cancel. Okay, and then we use our molar volume to go to moles, and then we can go from moles to grams. So this is really, really convenient for gas problems and reactions because we can convert from one thing to another and from moles to volume, from grams to volume, from liters to grams. We can do all this based upon the molar volume that any gas, any ideal gas at standard temperature and pressure occupies a volume of 22.4 liters per 1 mole. Thank you, and I'll see you in the next video.